Hello friends, we start a class on real sequence. This is our class 11, okay. In previous class we discussed so many important rules to find the limit of a real sequence, okay. And we discussed the null sequence and divergent sequences and so many types of divergent sequences with examples. In this class, we discuss two theorems on divergent sequences, okay? Two theorems on divergent sequences and two examples from MAPA, okay? We discussed two examples from MAPA. So first we write the theorem. Let xn be a real sequence. Then number 1, if xn diverges to plus infinity, then the sequence xn is unbounded above but bounded below. And number 2, if xn diverges to minus infinity, then xn is unbounded below but bounded above, okay. Clear? This is our theorems, okay. If xn is diverges to plus infinity, then it is unbounded above but bounded below, and if xn diverges to minus infinity, then it is unbounded below but bounded above, okay. We only prove this, okay, and similar process you can prove this. This is your SW, okay. So let us start the proof of one, okay. Since xn diverges to plus infinity, in previous class we discussed the definition when xn diverges to plus infinity, okay. So the definition is for each g greater than 0 however large, there exists a natural number k belongs to n such that xn is greater than equal to g for all n greater than equal to k, okay. This is the condition for a sequence diverges to plus infinity. For each g greater than 0 however large, there exists a natural number k belongs to n such that xn is greater than equal to g for all n greater than equal to k, okay. So for every positive number g, xn is greater than equal to g for all n greater than equal to k, okay. So we does not find, this implies we cannot find any number b belongs to R such that xn is less than equal to b for all n belongs to n, okay. We cannot find any b belongs to R such that xn is less than equal to b for all n belongs to n, because if we take any positive number, then there are some members of the sequence which is greater than g, okay. If we take any positive real number g, there are some member in the sequence which is greater than g. So we cannot find a particular real number such that every element is less than equal to that number of the sequence. Okay, this cannot be holds for any b. So this implies this sequence is not bounded above. Okay, this sequence is not bounded above. In previous class or in previous classes we discussed the definition of a bounded above sequence. Okay, when a sequence is called bounded above, this will discuss in previous class. Okay, now we have to prove that this is bounded below, because since we have to prove that the sequence is unbounded above but bounded below. So we already proved this is not bounded above, that is, this is unbounded above. Okay, this is unbounded above. Now we prove this is bounded below. Okay, since for every real number there exists a natural number k such that this condition holds. So if we take g equal to 1, then also there exists a natural number such as this condition holds. So we take g equal to 1, then there exists natural number, say m belongs to n, such that xn is greater than equal to g, that is 1, for all n greater than equal to m. Clear? For this is true for every g. So if you take g equal to 1, then there also exists natural number such that this condition holds. This condition holds. Okay. So this implies xm plus 1, xm plus 2, and so on, all elements after mth term of the sequence is greater than equal to 1. Okay, clear? Okay, so if we take a equal to minimum of x1, x2 dot xm minus 1 and 1. Okay, if you take a equal to minimum of this, there are m minus 1 term of the sequence, and we take a extra term 1. So this is a set of n real numbers. This is a finite set containing m elements. Okay, this is a finite set containing m elements. So if for every finite set has a maximum mem. Okay, so has a maximum and also has a minimum. Okay, so the minimum is exist as this set is finite. Okay, this minimum is exist as this set is finite. Okay, and a is less than equal to x1 comma x2 comma x3 and dot xm minus 1 also 1. Okay, this is as a is minimum, so a is less than equal to every element of this set. So a is less than equal to x1, a is less than equal to x2, a is less than equal to x3, a is less than equal to xm minus 1, also a is less than equal to 1, and a is less than equal to 1, which is also less than equal to 1 is also less than equal to xm plus 1, xm plus 2, and so on. So a is less than equal to x1 to xm minus 1, also a is less than equal to xm to so on. So combining these we have a less than equal to x1, x2, x3 dot 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 xm minus 1, xm, xm plus 1, and so on, all terms of the sequence. Okay, so this implies a is less than equal to xn for all n belongs to n. Okay, so this implies the sequence xn is bounded below. Clear? The sequence xn is bounded below. So we prove if a sequence diverges to plus infinity, then it is unbounded above but bounded below. Clear? By similar process and using the definition of a sequence diverges to minus infinity, we have to prove if a sequence diverges to minus infinity, then it is unbounded below but bounded above. Okay, similar process as one. Okay, this is your HW. Okay, now we discuss a work example from MAPA, page number 137. Okay, first we see this is 137 page and this is our work example. Okay, we discuss this. So what is our problem? If un be a real sequence and un plus 2 is defined by half of un plus 1 plus un for all n greater than equal to 1. Okay, and given 0 less than u1 less than u2, then we prove limit n tends to infinity un equal to this, that is the sequence un converges to 1 by 3 u1 plus 2 u2. Okay, so let us start. Since 0 less than u1 less than u2, so 0 less than u1 less than u2, this implies u2 minus u1 is greater than 0. Okay, u2 minus u1 is greater than 0. So now we find u3 minus u2. So u3. So from this relation, if n equal to 1, we get u3. For n equal to 1, we get u3. So put n equal to 1 in this relation, we get u3. u3 is half of u2 plus u1 minus u2. Okay, we put the value u3. Okay, this implies minus half of u2 plus half of u1. So this equal to minus half into u2 minus u1. Okay, now we find u4 minus u3 equal to half of u3 plus u2. We put n equal to 2 in this. Okay, in this relation, so we get u4. So u4 equal to this minus u3. So this is minus half of u3 minus u plus half of u2. This implies minus half into u3 minus u2. Okay, we put u3 minus u2 equal to minus half of this. So this is equal to minus half square u2 minus u1. Okay, clear? Again we find u5 minus u4. This is equal to half of u4 plus u3. Okay, u4 plus u3. If we put n equal to 3 here, then we get u5. So u5 equal to half of u4 plus u3 minus u4. This is equal to minus half of u4 minus u3. Okay, so this is, if we put this value, this will have minus half whole to cube u2 minus u1. Okay, similarly continue this process, we have un minus 1 equal to, see the similarity. Okay, first see the similarity. u3 minus u2, this is to the power 1. Okay, to the power 1, then to the power 2, then to the power 3. Okay, then to the power 3. Okay, 1 to the power 1 means just to the power 1. So u3 minus u2, this is 3 minus 2. We take this is 3 minus 2. 1 means 3 minus 2. This is 4 minus 2. So u3, so this is 3 minus 2. u4, this is 4 minus 2. Okay, this is 5, this is 5 minus 2. So un, we have, this is half to the power n minus half to the power n minus 2, u2 minus u1. Okay, by the similarity. Okay, clear? un n minus 2, u2 minus u1. Okay, now if we add this, we have, u3 cancel out. If we adding all this, u3 cancel out, u4 cancel out, u3 cancel out, u4 cancel out, similarly u5 cancel out, and similarly un minus 1 cancel out. Okay, only we get un minus u2. Okay, here only un and here only minus u2, and in the RHS we get this plus this plus this plus this. Okay, so we add all this, and we have, if we add all these, we have in left hand side we get first u3 minus u2 plus u4 minus u3 plus u5 minus u4 plus and plus un minus 1. Okay, in LHS is this, and in RHS equal to, in LHS we add LHS, and the RHS is this plus this plus this plus this. So first term is minus half whole to the power 1 into u2 minus u1 plus minus half whole to the power 2 u2 minus u1 plus minus half whole cube u2 minus u1 plus plus minus half whole to the power n minus 2 u2 minus u1. Clear? So if we add this, u3 cancel out, u4 cancel out, u5 cancel out, and then un minus 1 cancel out. Okay, so only we have un minus u2 equal to minus half whole to the power and common, u2 minus u1 is common, and main term is minus half whole to the power 1 plus minus half the square plus minus half the cube plus plus minus half to the power n minus 2. Clear? Now we have to find limit n tends to infinity un, that is un equal to u2 plus u2 minus u1 into minus half to the power 1 plus minus half to the power square plus plus minus half to the power n minus 2. Okay, clear? Now we get a result. Now we get a result Now we get a result 1 plus x square plus x cube plus dot 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 plus x to the power n. This is equal to 1 minus x to the power n plus 1 by 1 minus x. Okay, this is our result. If 1 plus x square plus x cube x to the power n equal to 1 minus x to the power n plus 1 by 1 minus x. Okay, so if here if x equal to minus half, from this to this x square x to the power n minus 2. Okay, so we add 1 and subtract 1. Okay, so this is equal to u2 plus u2 minus u1 into 1 plus minus up to the power 1 plus u2 plus u2 minus u1 into 1 plus minus half to the power 1 minus half to the power 1 minus half to the power square dot 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 minus half to the power n minus 2. Okay, minus 1. Okay, we add 1, subtract 1. So from this rule, this equal to u2 plus u2 minus u1 into this equal to 1 minus half to the power n minus 1. If here n, this is n plus 1. So here n minus 2, so n minus 2 plus 1, that is n minus 1 by 1 minus x. Here x is minus up, so is 1 minus up minus 1. Clear? u2 minus u1, sorry. Okay, so this implies u2 plus u2 minus u1 into 1 minus half whole to the power n minus 1 by 1, here 1 plus half, that is 3 by 2 minus 1. Clear? Okay, clear? So if we common now, this is un equal to this. Okay, un equal to this, so this is implies un equal to this. So if we now we find limit, therefore limit n tends to infinity un equal to limit n tends to infinity un equal to limit n tends to infinity this u2 plus u2 minus u1 into 1 minus half to the power n minus 1 by 3 by 2 minus 1. Okay, since u2 this all are constant, only the limit work on this. Okay, only the limit work on this part. Okay, clear? Only the limit work on this part. Okay, so we write limit n tends to infinity, sorry, u2 plus u2 minus u1 into 3 by 2 is 2 by 3 equal to limit n tends to infinity 1 minus half to the power 1 minus half to the power n minus 1 minus 1 minus 1. Okay, this, so this is 0. This is 0 because limit x to the power n equal to 0 for mod x less than 1. Okay, this rule we'll discuss in previous class. Okay, if mod x less than 1, then limit x to the power n equal to 0. So here is minus half, so mod of minus half is less than 1, so to the power n minus 1 converges to 0. So this limit this limit u2 plus u2 minus u1 into 2 by 3, this is 1 minus 0 minus 1. Okay, clear? Converges to 0 since limit n tends to infinity minus half to the power n minus 1 converges to 0. Okay, so if we calculate this, this is 2 by 3 minus 1. Okay, so u2 plus is equal to u2 plus u2 minus u1 into 2 by 3 minus 1. Clear? See, 2 by 3 minus 1. Okay, so this is equal to u2 plus u2 minus u1 into, this is 1 by 3. Okay, this is 1 by 3 minus 1 by 3, sorry, this is minus 1 by 3. Okay, so this implies if we get the LCM, this is 1 by 3 into 3u2 minus u2 plus u1. Okay, so this is equal to 1 by 3 into 2u2 plus u1. Clear? So limit n tends to infinity un equal to 1 by 3 2u2 plus u1. Therefore limit n tends to infinity un equal to 2u2 plus u1 1 by 3. Okay, so this is proved. Limit u1 equal to 1 by 3 u1 plus 2u2 proved. Okay, this is proved. Now we discuss another example from MAPA old book, page 138 of example 3. Okay, let's see the problem. This. Okay, a sequence even is defined by this. We prove limit even equal to 2. Okay, so we write the question. Even be real sequence. This is a real sequence defined by u1 equal to 2 and un plus 1 equal to root over of 2un for all n greater than equal to 1. Okay, prove that limit n tends to infinity un equal to 2. Okay, this is our problem. Let's start the solution. Okay, since u1 equal to root 2, so u2 is root 2 to the power half. Okay, u2 means root over of 2u1 by our definition. So this is equal to the power half into u1 to the power half, that is 2 to the power half. u1 to the power half means 2 to the power half whole to the power half, so that is 2 to the power 1 by 2 square. Okay, we put the value of u1, so this equal to 2 to the power half plus 1 by 2 square. Okay, similarly u3 to u2 by our definition, so this is equal to the power half into 2 to the power into u2 to the power half, so this is equal to 2 to the power half. We put the value of u2 is equal to 2 to the power 1 by 2 square plus 1 by 2 cube, so this is equal to 2 to the power 1 by 2 plus 1 by 2 square plus 1 by 2 cube. Okay, dot un equal to, you get 2 to the power half plus 2 square plus 2 cube plus 1 by 2 to the power n, because since this u1 to the power half to the power 1, u2 to the power 1 by 2 plus 1 by 2. For first term there are 1 term. For second term there are 2 in sum. For third term there are 3 in sum. For nth term there are n in sum. Okay, half square 1 by 2 or 1 by 2 to the power n. Clear? Now we find limit. Now we calculate this. Okay, so our un is 2 to the power 1 half plus 1 by 2 square plus 1 by 2 cube plus dot plus 1 by 2 to the power n. Okay, so this is equal to 2 to the power 1 plus half square plus half cube plus dot half to the power n. Okay, minus 1. Clear? We add 1 and subtract 1. In previous problem we discussed 1 plus x plus dot x to the power n equal to 1 minus x to the power n plus 1 by 1 minus x. Okay, so we apply this in this part. Okay, so 2 to the power 1 minus half to the power n plus 1 by 1 minus half minus 1. Clear? Okay, so this equal to 2 to the power 1 minus is equal to 1 by 2 to the power n into half. Okay, by 1 minus half means half minus 1. Okay, so this equal to 2 to the power 2 into 1 minus half to the power n into half minus 1. Okay, this is 2 to the power multiply 2 minus half to the power n minus 1. Okay, so if we calculate this 2 to the power 1 minus half to the power n. Okay, clear? Just calculation, easy calculation. Okay, so in previous classes we discussed some results, name as if a is greater than 0 and limit xn equal to L, then limit n tends to infinity a to the power xn equal to a to the power L, that is a to the power limit n tends to infinity xn. Okay, if xn is convergent then and a greater than 0, then limit n tends to infinity a to the power xn equal to a to the power limit xn. Since if we take xn, if we take xn equal to 1 minus half to the power and then limit n tends to infinity xn equal to 1 minus 0, because this is converges to 0, because if mod x is less than 1, this implies limit n tends to infinity x to the power n equal to 0. Okay, this is also a result. If mod x less than 1 implies limit n tends to infinity x to the power n equal to 0. This result also discussed in previous classes. Okay, so if x equal to half, then if x equal to half which is less than 1, then limit n tends to infinity half to the power n equal to 0, so this is converges to 0, so xn converges to 1. Okay, xn converges to 1. And if we take a equal to 2 which is greater than 0 and apply this result, we have limit n tends to infinity xn equal to limit n tends to infinity, sorry, this is un, this is un, equal to this 2 to the power 1 minus half to the power n. So this is equal to limit n tends to infinity, this is equal to the power limit n tends to infinity 1 minus half to the power n. Okay, so this is equal to the power 1 because this converges to 1, so this is equal to 2. Clear? So this sequence So the sequence even converges to 2. The sequence converges to 2. Clear? Okay, that's it. Thank you.